Okay, let's begin. It is my pleasure to introduce Otakar Svitek, who is a faculty member at Charles University in Prague. And today, Otakar is going to tell us about scalar field solutions in the Weyl class.
Thank you, David. Thank you, David. And thank you all for coming. So this work was done in collaboration with my soon-to-be finishing PhD student Lukáš and with my collaborator So the outline is the following. After some really good motivation, I will talk about the Weyl-scalar field system, about some symmetries that allow generate new solutions from known ones. And then, although we start with Weyl, so we start with axially symmetric class, we soon will specialize actually to spherically symmetric case of solution that kind of we analyzed with my PhD student, and the PhD student named it Spherical Curzon Chazy solution because it was generated out of the seed of Curzon Chazy. And since it will be a phantom scalar field solution, so we will see that there is wormhole throw, there is some strange singularity appearing. We will talk about its conformal structure and about the mass, how it behaves in such a space-time with phantom method. Since this spherical Curzon Chazy is essentially as well belongs to the class of genus Neumann-Winokur, so I will briefly mention genus Neumann-Winokur and mention what kind of limit one should take to get to our solution. And then I will show that surprisingly, although there is no Birkhoff theorem with a scalar field, so still this genus Neumann-Winokur family contains solutions that come from completely different classes. So one is this Weyl class, but then there is as well Robinson-Trautmann space-time solution with a scalar field, and some branch of the solution as well then belongs, the static branch belongs to the genus Neumann-Winokur. And then conclude. So the motivation is just that scalar fields are obviously kind of one of the simplest sources that one can have, and still they are reasonably physical, as one can see. At the same time, when one puts scalar field into spherically symmetric spacetime and studies static solutions, so there is one well-known problem with the regularity of horizons. So what happens is that generically you will have your horizon position, and it will be at the same time position of the curvature singularity. So you spoil the regularity of horizon and you made it into really singular hypersurface. Then in so-called ultrastatic cases, this is not the case, but essentially ultrastatic cases lead to naked singularities. So one can as well use, or it was used frequently, the scalar field spacetimes to discuss such cases like cosmological censorship hypothesis and so on. Since we are dealing with the phantom scalar field, so this will inevitably lead to kind of wormhole spacetime. And also, of course, our initial idea with the student was, okay, so let's study these properties, especially related to regularity of horizon, in something a little bit more general than spherical symmetry. So we started with the Weyl geometry, but then we found relatively nice looking solution that is essentially spherically symmetric. So in the end, we studied especially this one. So we have standard Einstein-Hilbert action with free massless scalar field. And of course, we arrived at these equations of motions. And here, this epsilon parameter encodes our choice of either having standard scalar field satisfying energy conditions, or having with -1 scalar field that has a kinetic term of opposite sign. And that's why violates all the energy conditions. And the geometry ansatz is the Weyl one. And you see, of course, maybe the most important is to notice now that once this k function becomes 0, so you recover spherical symmetry. So this will be, in the end, our choice how to proceed. And when we plug this ansatz into field equation, so we arrive at this system of equations for both the metric functions and the scalar. So immediately we see that the function u and the scalar field satisfy the same equation, and namely it's evidently just flat space Laplace equation in cylindrical coordinates, which means that this family was used quite frequently, since one has plenty of possible solutions for the Laplace equation in flat space, and one can use it to construct a GR solution. And how one would do it? So if one would solve both of these, so then you plug the results here, and then you simply like trivially integrate the k, and you have the full geometry. Another thing to notice is that apart from u and phi having exactly the same equation to satisfy, so they appear as well quite symmetrically in the equations for k. So this immediately leads to those symmetries that we will be talking about. And the simplest solution of this class is, of course, when you take, and let's say we are in vacuum, so we have phi 0. And of course, the simple solution for this is just Newtonian potential for u. And then for Newtonian potential, you recover k like this, and where r is given by this combination. And this is the famous Curzon Chazy solution. And why? And of course, in this Weyl class, it looks much simpler than the Schwarzschild solution, because Schwarzschild solution would correspond to the potential of a rod. So when this seems, it should be much simpler solution than Schwarzschild. But then when you discover that k is non-zero, so it means it's not spherical symmetric. And most importantly, there is kind of weird singularity at the origin. Namely, if you approach the singularity in equatorial plane, then you really hit the singularity, while if you go along the axis, so you don't see the singularity, and you can actually extend the space-time to another copy of it. So that's why this is not that much useful physically as a solution compared to Schwarzschild. And as I was mentioning, the symmetry between u and phi was used by Gibbons and Volkov to kind of summarize all kinds of symmetries that can be read off from the system. And of course, the idea is once you have symmetries between these fields, so you can use them to generate new solutions out of old ones. So this is really what they propose. And if one has a standard scalar field, so the symmetry, we look back, but we don't, the symmetry is evidently rotation. So you can rotate your, for example, initial u and phi to this new combination, and this new combination for phi. Evidently, we can, in this way, get rid of the metric function u by putting the parameter of the rotation to pi half. So we will have no u, and we will have just phi, but we will have non-zero k. So we will have kind of ultrastatic solution. Ultrastatic means here that the stationary killing field is as well covariantly constant. So the kind of the killing equation is trivial because both terms are 0. So we get like this ultrastatic. If we have phantom scalar field, so the symmetry is boost. And then there is another symmetry, the swap symmetry, but that's possible only for the phantom scalar field, where we flip u for phi and switch the sign of k. And this can be used for, again, getting ultrastatic solution out of Curzon Chazy. but we will now concentrate on its rotations and boosts. Ultrastatic, as I was saying, that the stationary killing field is covariantly constant. That each term in killing equation is by itself 0 automatically. One doesn't need to symmetrize. So, so now we do this rotation or boost of the original Curzon Chazy solution. So it's vacuum solution, and now by this boosting or rotating, we will induce non-trivial scalar field. And this is, and we encoded this parameter of rotation in case of real scalar field and the standard one, and in terms of the phantom scalar field, which is given by this boost. So we both describe with this parameter. And then we generate a new solution of this form, and immediately receive, since this epsilon parameter appears under the square root. So for standard scalar field, we need to have S limited like this. So we can, for example, make limit S going to infinity. And again, evidently, we will kill U, and we will preserve phi and S K. So we will have non-spherically symmetric but ultrastatic solution. But there is another limit possible, and that's for the phantom scalar field, where the S should be less than 1. But this limit first needs some redefinition. So this parameter M that should represent the mass, we will make it into some small n times the parameter S, and we send this S to 0. So now we input it, we see that U gets preserved in the form M over R, and phi gets preserved in a similar form. But in this limit, since here the M is not divided by anything, so this limit, of course, cancels the K. So we will arrive at a spherically symmetric solution. And moreover, when one computes the Kretschmann scalar of such solution, so we immediately realize that it becomes regular.
Question. S goes to infinity, means U goes to 0. First.
Here. Yeah. So this M will be now small n times S. The S go away, so it will be small m over R, just. So yeah, if we don't do this kind of rescaling of mass, so yeah, this would and the K disappears because there is no S here to compensate.
Yeah. What can we say?
Yeah. I will have it immediately. So just, yeah, the Kretschmann scalar becomes regular everywhere, and the line element looks like this. So we have Newtonian-like scalar field, and then we have such a line element with these exponentials. So it is spherically symmetric. Later, I will show what kind of limit of this Janice-Newman-Winokur, or sometimes now recently Fisher-Janice-Newman-Winokur solution one should make in order to recover this solution. It behaves asymptotically like Schwarzschild, and at R equals 0, both GTT and GRR metric functions behave similarly to how they behave in Schwarzschild on the horizon. But then when we kind of study the aerial radius, here, so then we see that it diverges at R equals 0. So kind of R equals 0 seems to be like the copy of R equals infinity. And it has its minimum at R equals M. And of course, then we were immediately thinking, okay, so this is probably the wormhole throat that separates the region of R less than M from the region of R bigger than M. So from this discussion, it seems like it looks really different than Schwarzschild, especially for small r. Asymptotically, yeah, there is some like similarity to asymptotic behavior of Schwarzschild, but for small r it does not. And then since referee forced us, so we as well computed how the photon sphere and innermost stable circular orbit looks like. And what we found is that both of them are within 10% of the Schwarzschild values. So it's pretty close to Schwarzschild. And of course, one has to compare it using aerial radios to have proper result. And especially, I think the photon sphere was like 10%, and ISCO was like even 5% away from the Schwarzschild values. Then what we can see is, okay, we have, this is evidently a solution of Laplace equation. Here we point-like solution. Here we have as well in exponential this U function solution of point-like sorts for Laplace equation. So then naturally one can think about the solutions that would be composed from many of point sources arbitrarily distributed. And then one can really see that it will all work out, and the gravitational attraction of these, basically, let's say, wormhole throats will be compensated by the repulsion of the phantom scalar field. So we will have this kind of phantom scalar field version of Majumdar-Papapetrou-like solutions, which contain multiple black holes that are kept separate by the electrostatic repulsion. No, this is of course Majumdar-Papapetrou. This one is wormhole. Yeah. It's yeah. We will now we will look at it, and indeed when we take these null vectors and compute, and of course these are radially pointing null vectors, and we compute their expansions, so we can immediately check that they satisfy the conditions of being wormhole throat. Namely, this of course condition you all know, because this is the same condition for locating quasi-local horizons, and it's as well the same condition for essentially locating places that are suspicious of being wormhole throat. But then there is another condition that is called so-called flare-out condition, and this basically means that the wormhole throat really works in the way that it will kind of attract you to the throat from one side and spews you on the other side. And this is symmetric. So for the other, this is here just for the congruence K. But if you compute it for L, so it's behaving in the same way. So basically, on one side of the throat, you have the ingoing, let's say, K congruence that has negative expansion. Once it passes the throat, it becomes having positive expansion, and the L is exactly inverse of it. And yeah, and then of course we made as well some embedding diagrams, and also already from the embedding diagram, so one sees that this is not that we would not be really this much unable to extend it more, but there is really some problem that both sides are not completely symmetric. Close to the throat, it looks really pretty symmetric, but away from the throat, things are getting a bit more complicated. So we were not able to extend it, the embedding more. Mm-hmm.
The solution 5 is what for the minus
yeah.
Is it for
this is this phantom scalar field? Yeah. The
both us. Both are
yeah, because it appears quadratically in T mu nu. So yeah.
This is the near the throat. How does the TT component of Weyl look?
Near the throat, yeah, we can throat its R equals M, so it will e to minus 2. So it's some finite value. Yeah.
You said that you couldn't extend the embedding diagram further. Do you know if both ends are asymptotically flat?
I will get to it.
Everybody's asking questions, but they're on the next slide. You've anticipated it.
So, so this is exactly about the other side, and yeah, so now we are investigating this R equals 0, and this R equals 0 is first null hypersurface, but as well, curiously, all curvature invariants are vanishing there, which is not kind of automatically clear since the scalar field diverges there. So definitely this should not be asymptotically flat end because the scalar field diverges there. But still all the curvature invariants are vanishing. On the other hand, radial time-like and null geodesics are incomplete there. So in the left part, left away from the throat, let's say, so the time-like and null geodesics are incomplete, while the proper distance to R equals 0 is infinite. So something is in infinite distance, but in principle you can get there in finite time as a time-like observer. So there is something strange happening. And although the curvature invariants are vanishing, but some components of Riemann tensor in parallel propagated and radially in falling frame to this position R equals 0 really diverge. So observer really experiences infinite tidal forces. So it's not.
Since it's belongs to the spectral class, it's some terminology relate variety.
Sorry.
Also, when in the regional frame components are finite, but for
I mean, yeah, in some standard classification, they usually call this non-scalar singularity, exactly because the scalar invariants are vanishing, but still there are like tetrad components of Riemann tensor that blow up for like standard observer. So they usually call this non-scalar singularity. Yeah. And of course, one can trace the appearance of this singular behavior of Riemann tensor back to the Ricci part of Riemann. And of course, it's directly caused by this scalar field blow up. Yeah, so then we were constructing the conformal. Yeah, but yeah, it depends. Yeah, the fact that this scalar, all the scalar quantities are 0 is a bit strange. Definitely, it's not something that one meets frequently. Yeah. So we constructed the conformal factor in order to provide some conformal picture of our spacetime, and it satisfies the conditions in order to be asymptotically simple. Yeah, I can find it, but it's yeah. So it's in the paper. Yeah. And it's not something crazy. And but type N, the solution is of type D. Okay. Yeah. And so these we of course first check on the side that one would consider that would be asymptotically potentially even flat, the side where the scalar field vanishes asymptotically. So there one is not surprised that at least it's asymptotically simple, but surprisingly the same is true as well at that non-scalar singularity. So even there the omega factor satisfies these conditions for being asymptotically simple. But even in that R infinity end, still the spacetime is not asymptotically empty. Namely, the scalar field decays too slow. So it's asymptotically simple, but not asymptotically flat because of small decay of the scalar field. Yeah, and so this is the conformal diagram. So this part is asymptotically simple, but essentially even this part is asymptotically simple. But here you have this non-scalar singularity first, and second, here we have pictured some in blue are the time-like geodesics, and in red are constantly accelerated observers, and the green, the middle line, is of course the wormhole throat. So one sees that it's reasonably symmetric between the left and right part along the wormhole throat, but one can see that we would have to blow it up more, but definitely these time-like geodesics are approaching this kind of surface in slightly different fashion than here. So it's not completely symmetric, especially when we go close to the singular hypersurface. Asymptotically simple was these two conditions for the conformal factor of the compactification. That of course it's non-degenerate on scries, and it's condition at space like infinity. So, and now
R equals 0 is actually used in sphere.
yeah, R equals 0 is really in terms of the geometry of the transversal space of the sphere is really kind of similar to this. Yeah, yeah. Yeah, yeah. Yeah, it is somehow strangely similar. Yeah. But what is more important is that those geodesics that go to this part that contains this strange singularity, so they get to I plus at a finite time. So you can if you, of course here it's not like this. Here if you are in the like this right hand part, so here the geodesic will take infinite time to reach I plus, the time like geodesic. But here, let's say I start from here, so this really has only finite proper time of the observer. So it means that by going into this wormhole, and essentially we were able to kind of localize that the effect, of course, is stronger the closer you approach the singularity. So then you would have to go closer enough, but then kind of accelerate in order to get out of this part. But then you would be able to reach future time like infinity in finite time using the inside of the wormhole. So it's kind of like, and of course it works just like this. You cannot, there is no way how to turn around. So it's just one directional time machine. You can get to far distant future by going through this wormhole.
And what happens near the R equal to 0 here?
R equals 0 here. This is R equals to M, the wormhole throat, and there is nothing strange happening. This is like wormhole throat is basically like quasi-local horizon. It's as well not some special place that one would notice anything necessarily. Of course, one can do local experiment to see, but it's not something drastic.
And R is strictly positive here.
R is from 0 to infinity, and here is R equals M. Yeah.
This question. So, typically in wormhole solutions, you have this proof of a minimum.
Yeah, we have at the throat we have minimal aerial minimum area. Yeah, the throat is really the surface of minimal area, and then it becomes bigger as you go here, but as well as you go here.
So R equals 0.
So R equals 0, really the sphere is infinitely big. This is because of that exponential factor. Yeah.
And its area tends to infinity.
Yeah, here the area is infinite again, like here, of the spheres. Yeah. So then we were as well trying to compute the mass of the spacetime in order to give some physical interpretation of the parameter m. And so we compute all these Komar, ADM, and Brown-Muir masses, and they all give mass equal to m. So that parameter is really kind of asymptotic. And of course, this was computed on that right side. So this was computed on the spheres here. Yeah.
Yeah, since you have 1 minus 1 over R.
Yeah, of course. So this was not surprising. Only one has to be careful because both this Brown-York and ADM mass, they contain like these regularization counterterms that you subtract Minkowski values. So one has to make sure that one uses comparable coordinate sets. Otherwise, this subtraction will not work, and one can easily get like wrong factor in front of m. But otherwise, other than that, yeah, it's quite straightforward. And of course, then one would like to see as well where is this mass and how exactly is distributed throughout this spacetime. And for this, these definitions, especially like Komar and Brown-York, where you can select the sphere where you make the computation, so it's insensitive to the radius. So irrespective of radius, you always get m. So you cannot use these to kind of try to localize where is the mass really in the spacetime. So then there is another definition of mass or energy in the spacetime that works only in spherical symmetric cases, and it's Misner energy, and it basically should give the energy contained within the sphere of given radius. And for our spacetime, it looks like this. So this is a plot for m equals to 1. So it means that throat is here. So we see that the maximum Misner sharp mass is at the throat. And then it decreases, and asymptotically it gets to 1, which means to m. So asymptotic mass of even the Misner sharp mass will be still m, but it's not the biggest one at infinity. The biggest one is at the throat. And then, of course, one can use this to compute as well, like the density distribution of this energy. And one gets this plot. So, and of course, this is corresponding to the first one. So at the throat, you have 0 density, and then the density becomes negative. So this, of course, corresponds to the place which is here, and then kind of the phantom scalar field energy starts to dominate and decreases the energy of the spacetime as you go to infinity. And as well, what is evident is that inside the wormhole, surprisingly, we have positive energy density. And the negative energy density is hidden outside. So inside kind of the gravitational, let's say, energy, if one can uniquely define it, would be dominant over the negative energy of the scalar field. But outside the throat, it exactly changes.
You could also compute those cuts.
Yeah, we were as well.
Send it by the chat.
Yeah. We did as well this in the paper. Yeah. But there the picture is much more complicated. So one has to be even more careful. So yeah, this needs a deeper description of the situation. But yeah, we did it. Yeah.
Something here seems a little confusing to me. So you started off with this other space-time with presumably the big M parameter was also mass.
Yeah.
And then you scaled that down. That should be, that parameter is 0 now, right? In this limit.
Yeah.
So how am I supposed to understand the relationship between the original big M and this one, if they're both ADM mass, or if they're both Komar-Brown-York mass? But
Oh, I'm not completely sure if one, but hopefully one would get that big M as a mass of that one, because that one is not spherically symmetric. So yeah,
right,
one
so the
would
calculation is hard.
and one would not able to use this Misner-Sharp energy.
Mhm.
So, but yeah, but this is it. I mean, always space-time limits are producing many times weird stuff. So you cannot do like parameter limit in your metric and assume that that kind of the geometry smoothly changes into some
Right, right.
final state.
So-
There can
so-
really be like complete disconnection between those with away from limit and those in the limit.
Okay, so it's a singular limit. That's the,
Yeah,
in some sense,
yeah,
it's singular. Thank you.
So as I was mentioning, now I will show you the Janis-Newman-Winokur solution that I already announced before. This solution was essentially rediscovered historically many times, and the first one was already at 38 Fisher, but then Janis-Newman-Winokur discovered it again without knowing about work on Fisher. Who was Fisher? Fisher was Russian, and so I think the paper was. I'm not sure when it was translated, so there was this problem of language barrier as well. So that's why in the West it was for a long time not known that it was discovered already before. But even then there is Wyman solution, and he evidently is unaware both of Fisher and Winokur. So it was really rediscovered many times in this kind of solution. Although Wyman gave as well some kind of dynamical generalization apart from just the static solution. So this is the static solution with again free massless scalar field, and we see that okay, we have this metric function and we have two parameters. So we have the mass and we have parameter s, and this parameter s is kind of tied to the strength of the scalar field. So we have one parameter that is more for the like mass of the space-time, and one parameter that specifically kind of gauges how much scalar field there is. And I already generalized it to potentially phantom scalar field with this example here. And we immediately see that if this is negative, so we can make again s goes to 0 limit. And again, reparameterizing. So I already brought this line element into the form where one can do essentially the same limit that we did before, and one recovers our so-called spherical Curzon Chazy solution. So this is one example where this solution kind of contains static spherically symmetric scalar field solutions that are found in different families. And now I will give another example. There is so-called Robinson-Trautmann class of geometries, which is fairly general class that is defined just by the presence of congruence that is non-shearing, non-twisting, but expanding. And based on this geometrical assumption, one can derive the general form of metric, especially in vacuum. And this solution can be thought of as like class that generalizes into non-rotating solutions, Schwarzschild, Weyl, or symmetric. So one can have some deformed Schwarzschild solution but deformation that is non-rotating, or deformed Weyl, and so on. And the vacuum version of this solution, the one that was discovered by Robinson and Trautmann. So for this vacuum version, it took, as you see, more than 30 years to properly analyze its meaning. So now I will skip to the space-time diagram. So this is the vacuum Robinson-Trautmann solution. And what is the meaning is that, okay, only this portion is really the Robinson-Trautmann spacetime. It is set up such that at some finite retarded time, you give initial data for the solution, and then you evolve it. The Robinson-Trautmann geometry is such that your Einstein equation is reduced to just single equation that is of parabolic time, fourth order parabolic equation, which means that such equation, and of course the time of this equation is exactly this u, this retarded time that grows like this on these null hypersurfaces. And since you have parabolic equation, so it of course has nicely behaved solution in one direction, but completely blows in the other direction. So that's why for generic Robinson-Trautmann, you cannot evolve it back to arrive at scribe minus, because the solution will blow up. So you can only give the initial data and evolve it to the future.
What is the relation with the metric which you described before?
No, this is different solution. This is just another example from completely different class that again arrives at this Janis-Newman-Winnick. So this is like second part, let's say, but I want to stress that even other solution from completely different classes of geometries arrive surprisingly at this Janis-Newman-Winnick class. So although there is no uniqueness, still surprisingly many solutions are contained in that. Yeah, so what one can imagine is here I will give data that would represent some nonlinear deformation of Schwarzschild. Only the deformation should be such that there is no rotation into it. And then this highly deformed Schwarzschild will evolve in such a way that it will radiate gravitational waves. And by radiating gravitational waves, it will become more spherical and more spherical until at this u equals infinity, it basically is almost completely spherical. And in this u coordinate, this kind of evolution is behaving that you achieve the sphericity exponentially fast. So it's really fast radiating away the gravitational waves, and you achieve the spherical symmetry. And of course, since it's dynamical here, so you cannot easily extend here event horizon because you don't have fast scribe. So you typically localize some quasi-local horizons, and then once you become here completely spherical symmetry, so you are basically Schwarzschild. So natural thing is to extend it by inner Schwarzschild solution. But since this exponential decay has it's some series that contains exponents of different order in this exponential, but in some terms there appear as well polynomial terms, and these polynomial terms mean that this extension cannot be made smooth. So you have non-smooth extension to this, and this can be generalized, of course, to cosmological constant. Surprisingly, for cosmological constant, for some specially calibrated value of cosmological constant with respect to the mass of that Schwarzschild-like spacetime at the end, you can find the case where it becomes really smooth. So you can make, for specifically tuned values, you can make smooth extension and to prolong it.
Okay, how smooth?
Well, again, it depends. So typically for vacuum, I think the no smoothness was
There is no shell.
C127 appearing, and these kind of crazy numbers. Yeah. But then it depends on the exact values of the parameters. But yeah, there are these kind of crazy numbers. But as well with when you have null, apart from the gravitational waves, you can have as well null radiation going out. So you can have like Weyl generalization. So there you can hardly achieve even C2 extension. So it's really very substantial. So this is kind of the picture of the vacuum that one can have in mind. And okay. And one more thing that might be interesting for people doing gravitational waves here, that this space-time was as well used to explain anti-kick in the binary mergers, because, okay, here you have some highly deformed Schwarzschild, so you can imagine that it's after merger, after already you have common horizon enveloping both of those black holes. So it's of course highly distorted, but you can describe it in this family, provided that of course it's not rotating too much, that you can neglect the rotation. But then if you have a big black hole and small black hole, so the geometry of the common enveloping horizon will be such that the maximum of curvature of the horizon will be close to that small component of those two, because you will have kind of like this. And then in this space-time, you can compute really asymptotic momentum. And you can see that this asymptotic momentum is highest exactly in the direction when you have highest curvature on the horizon. So then it means that kind of the kick is exactly opposite that you would think, that it's like going after the smaller component. And this is, no, that is, yeah, the gravitational waves are going predominantly in the direction of the small component and the system moves the other way. So this is, yeah, mention this. So then we generalize this to scalar field. And for scalar field, we had to change the ansatz of the metric. So for vacuum, here you would have just this small r squared. And this provides you with too much restricted Ricci type of the geometry. So when we made this ansatz, so we extended the Ricci type of this Robinson-Trautmann geometry, and then we were able to input the scalar field that depends on this two coordinates, and it was non-aligned. This is just how it looks like, but that's not too much important. The properties that it has. So now you have basically as a source of your geometry just the scalar field. And the scalar field makes, again, as in the vacuum, a singularity that is present for all retarded times. But curiously, the singularity is initially naked, and only in later retarded times, it becomes covered by a quasi-local horizon, which is the same as, for example, in Weyl. In Weyl, one can as well have cases that behave similarly. So it's not completely strange. And then when one evaluates how the asymptotic behavior of the solution looks like, namely this U infinity limit, so one realizes that one does not attain any black hole type space-time, but one attains really something that is just flat.
This is what they call quasi-local horizon.
A quasi-local horizon is the place where you kind of search for some surface which has a vanishing expansion of null rays emanating perpendicular normal to the surface.
What is the difference between quasi-local
and even horizon. Even horizon, you need a complete evolution up to Scry, because it's like past of Scry, light cone, and so on. But here you don't need to evolve the space-time completely. You just can localize it really in the given place, quasi-locally, because you need the complete surface. There are even local definitions using just some curvature invariants, but so far they are not that much successful. So yeah, as I was saying, we end up with flat. And as well the scalar field, of course, naturally vanishes, so there are no scalar hair left. And as well, the body mass decreases smoothly to 0. So this would be in terms of the spacetimes that one studies for this collapse of scalar field, automatically just the spacetime that where the scalar field disperses completely. So there is, in this class, there is no possibility of really forming the black hole out of the scalar field. The scalar field always disperses. But apart from this generic case, depending on the values of constant, we have two additional special cases. One is spherically symmetric, but still dynamic solution, and it becomes as well a relatively non-Robert solution, which has, again, depending on the values, it can have naked singularity for some values, it can have singularity that is enveloped by horizon for other values. But as well, in the simplest case, it contains such ultrastatic solution, and this, together with this scalar field, so you see this is really extremely simple geometry, and again can be obtained as infinity limit of the Janis-Newman-Winnicourt that I was talking about. So one can obtain even this ultrastatic solution, although it comes from completely different family from this Janis-Newman-Winnicourt. Okay, so this is my last slide basically. So I showed the spherical Curzon Chazy solution that we discussed with a PhD student. And we showed that it behaves like wormhole, but as well like unidirectional time machine, in a sense, allowing you to travel to infinite future in finite time. And it contains weird non-scalar singularity. And basically, this weird non-scalar singularity is the source of this time machine-like behavior. And this solution can be obtained as a limit of this Janis-Newman-Winnicourt solution. But there are as well other completely unrelated classes, like the Robinson-Trautmann class, when we generalize it to massless scalar field. So again, the static solution, the static branch of this one is again contained in this family. So this work is related to this spherical Curzon Chazy, and these two are all the works related to this Robinson-Trautmann scalar field. Thank you.
Thanks, Otter. Do we have any more questions?
Symmetry is the first part of the talk. R equal to 0. This part is directly the horizon was the infinite area, right?
Yeah, but it's look like a bit like horizon when just one studies the metric function, so they behave like they would behave on horizon of Schwarzschild. But at the same time, it's not good horizon because it's singular in some sense.
Requires infinite time.
No. This R equals 0 is infinitely distant in like for spatial geodesics. So, but it's finite proper time for time-like observers. So they can get to close to it in finite proper time. Yeah. So they are really they kind of or even null geodesics really arrive there at finite a fine parameter. So in principle, it looks like they should be one should be able to extend it, but one is not because there is this strange non-scalar singularity. Yeah, but
if there is no space-time singularity,
no, there is this non-scalar singularity.
non-scalar, but no space-time.
No, it's space-time singularity because yeah. Yeah.
More questions?
But to reach it is not.
You reach it.
Square does
No, the scalars are all finite. Yeah. Yeah, but then why should one extend something that has in some radially infalling, parallelly propagated frame has some components of Riemann diverging, meaning that there are infinite tidal forces?
the other side. You can start on the other side. This kind of things is called negative horizons.
Yeah, but usually these are even with
Extend. So it's a black hole actually. It's also a black hole. It's a wormhole with a black hole
On the other side.
on the other side. I think you are not done with that.
But yeah, the question is whether one really should go beyond something. Okay. But you think it makes sense to really extend it, although some observers can experience infinite tidal forces? Yeah.
Can be on the other side.
Okay.
Then,
Okay.
and even that a particle, what particle does not get, that does not feel like infinite.
Yeah.
Finite objects.
Okay.
That's a good point.
Any more questions? I was curious about in the Robinson-Troutman setup. So if you were solving something hyperbolic here, then you'd have to give data both on the U equals initial, but also you'd have to, give data on some transverse null slice.
Yeah.
Instead here it seems like you'd have to give singular data down at the bottom. Is that what happens?
Yeah, exactly. You have really already here the singularity.
Okay, so
Yeah,
the initial data, so you have to solve
the-
although it's nice and parabolic,
Yeah,
everything
yeah.
should get smooth. You have to give singular data.
Yeah. That's origin. Yeah, exactly.
Thank you.
What happens between consideration interaction of particle with scalar field?
Oh, this we
Some scalar.
yeah, we haven't studied this at all. No. But yeah, of course, since in that space-time the scalar field is phantom one, so yeah, it can be interesting because it will counteract some gravitational attractions. Yeah.
Yeah, you can extend to R to minus infinity.
Mhm.
Symmetric, right?
Yeah.
Black hole,
Yeah, this would be good.
Oh, there you go. You have a mission. Okay. Do we have any more questions?
Your energy conditions are all fine, right? The energy conditions, they are all fine.
For the previous solution.
Yeah, I mean for the ultrastatic solution printer, it's like super nice and simple. Is that one like the energy conditions are?
No, of course, for this, the scalar field here is phantom.
Oh, okay.
Yeah, so it violates everything.
Okay.
Yeah, otherwise you wouldn't have.
Well, if there are no more questions, let's thank Otter again.
If you enjoyed the video, like and subscribe.